right, let's get started. I'm going to finish up the stuff we're talking about with hypothesis testing and false discovery rate stuff today. And then Wednesday and Friday we'll start talking about more exploratory techniques that you can do with data like these. Specifically, cluster analysis to explore structure between samples or replicates, principal component analysis, and a related technique called singular value decomposition for, again, exploring structure among multivariate data. And then just some basic detective type things to look at when you have some of these data. Looking for outliers, assessing how much missing values there are, finding unusual patterns and features that maybe are worth looking into further. Like all of the samples that were run by technician X differ from those that were run by technician Y. But today we'll finish talking about this process of doing a test for each of our features. Thousands of features. We're going to go through and do a t-test or regression or an f-test or something and get p-values for all of them, and then we want to convert those p-values to something that's more flexible than p-values, more flexible than type 1 error rates, and that's the false discovery rate. So I am in testing.r again, and we've just got a little more code to go through. I'm going to simulate our data again and go ahead and put in some differential expression. So we're creating 1,000 features, just made up data, simulated data, and the first 300 features are set up to have differential expression. So that means the mean for each of the first 300 rows, the mean in comparison group 1 is different from that in comparison group 2. The rest of the features, the rest of the 700, or the 700 remaining ones, do not differ between the comparison groups. So looking through, doing tests, and searching for interesting features, ideally we would find the first 300 and none of the last 700. In practice, we'll have true interesting features and true null or uninteresting features, but we won't know which ones are which, so we have to use our statistics to try to find them. Okay. Let's compute the p-values. If we do a 2-sample t-test comparing the representatives from the different groups, so 1 p-value per feature. This was our histogram of p-values. And remember limitations on working with p-values. If we select features based on having a p-value less than 0.05, then all we can say is that the probability that a null feature gets selected doing what we're doing is 0.05. So I expect no more than 5% of the null features to have been selected into this list right here. So I have 148 features that were called significant based on a p-value less than 0.05. These are unadjusted p-values, so the multiple testing cautions apply. We found 148. That's different from what we saw last week, by the way, because we're doing simulation, and I just re-simulated data. So the numbers will be a little bit different. 148, you hand that to your biologist collaborator and say, these are the ones that I think are worth looking at further. And if you were asked, how confident are you in these 148? All we could say at this point, having just done p-values, is I expect that no more than 5% of the null features, we started with 1,000, and some of them, some proportion of those 1,000 are null features, not interesting. I expect no more than 5% of them to have been selected into this 148. But that's of limited value in terms of a statement about confidence, because what if all of the features were null? What if all the features were null? Then you would expect a lot of these 148 that we found to be null. If all the features were null, we would expect about 5% of them to be selected just by chance. So that would be 50 features. So I would expect 50 out of these 150, 50 out of 148 to be null. But what if only 10% of the features were null? That means 100 were null, and we expect no more than 5% of the null ones to be selected into this list. I would expect no more than 5 of these 148 to be false discoveries. So what I get to say with p-values is just, if you were to redo this procedure, whatever number of null features there are, I expect to get 5% of them into my list of 148. But the actual confidence that gives you about this 148, it depends on how much signal there is in the data in the first place. So my point is that p-values and type 1 error rates are kind of limited in what they tell you. What you would like to do is say, here's 148 features out of the 1,000, and I'm 95% confident in them. You want to be able to say something like that. Type 1 error rates and p-values don't really apply well. False discovery rates do. All right. So how could we translate this into false discovery rates? That's what we talked about last time. And it has a lot to do with this picture that we made of the p-value histogram, because we said that picture is a mixture of two components. There's a flat histogram sitting behind the scenes, and then there's a histogram that's packed up over at 0 sitting behind the scenes. And those have been mixed together. And in particular, the height of the flat part, if all the features were null, the height of the flat part of this distribution would be 1. To the extent that it's not 1, that tells us about the trade-off between interesting and uninteresting features. So in the paper that we were looking at, that Story 2003 paper, we said we can convert these p-values to a false discovery rate. For this 148 features that had p-values less than 0.05, if I can estimate the proportion of my 1,000 features that are null, then I can convert this result into an estimated false discovery rate. The key there, here's the histogram we're going to look at. It needs to be a probability histogram, not a frequency histogram. Looks qualitatively the same, but now it's scaled so that it looks comparable to a probability distribution or density function. Dashed horizontal line is at 1.0. That's what I expect the height to be if there was absolutely nothing interesting in these data. So if we estimate what the kind of average height is for the flat part, that's this pi 0 with a hat on top. pi 0 hat. I want to estimate that. And if we have pi 0 hat, we said in the paper last time, we can estimate the false discovery rate. So if we're going to use a p-value threshold of 0.05, say, then the estimated FDR for the features that we pick out applying that threshold is pi 0 hat, the estimated proportion of null features, times the number of features times the p-value threshold divided by the number of features that had p-values below that p-value threshold. That came straight from the paper. My estimate of the average of the ratio number of false positives divided by total number of positives. So I want to estimate pi 0. And one kind of quick and dirty way to do that would be to just look at the heights of these bins, these rectangles, and just average up the heights of the part of the picture where we think it's flat. So in this HH object, I assigned the output of hist to an object called HH. And HH has some elements inside of it. Like density contains the heights of these rectangles. So the first rectangle in the picture has height 2.02. The next one drops down to 1.14. And then there's all of these. So what I'm going to do in the code is just roughly ballpark this and say, let's take the bins. Let's take all the bins except the first two. And let's consider all of the remaining ones except for the first two as reflecting the flat part of the distribution. So I'm going to pull out, I want the heights of all of these rectangles, average those up, call it pi 0 hat. That's what this is going to do. So pi 0 hat is the average of those that density element of the hist output, and just take the 3rd through the 10th one, because those are the heights of these rectangles. I'm going to leave out the first two because I think that includes a lot of the differentially expressed features. I just want the height of the flat part. What about what? This one right here? You know, these are like sample realizations of an underlying reality. Because there's sample realizations, there's plus and minus, that's just random. If I were to redo this by getting a new sample and getting p-values and remaking this, that particular bar that's a little higher than 1 might well have dropped down below 1. So I'm looking at the right part, everything but the first two bins, and I'm saying, roughly speaking, I think those are kind of constant and they're just bobbing around a little bit randomly. That's why I'm going to average their height values. So if this one's a little high, probably, that one's a little low, probably. So I'm kind of hoping they'll average out to a good estimate. So let's compute pi 0 hat. 0.855. So that is based on that estimate, I estimate that about 15% of my features are interesting. 85% of them are not. And then we can convert to an FDR. Let's convert to lots of FDRs. Let's consider a variety of FDRs as a function of p-value cutoffs. Because we said last time that we may want to consider what the trade-off is between FDR and the number of features that we get back to investigate further. Maybe I can stomach a little bit extra error if I get lots of extra features. So let's make a picture like one we saw in that paper, which is going to be, we'll make two pictures. One is going to be a bunch of p-value threshold possibilities. Let's draw the threshold at 0.01. Let's draw the threshold at 0.05, 0.1, dot, dot, dot. For each one of those, let's compute the estimated FDR. So if we did use a p-value threshold of 0.05 and we got these 148 features, what would be the corresponding false discovery rate for that? That's what I'm doing here. Let's compute for a variety of p-value threshold possibilities. Start at 0.01 and go all the way up to 1 with 100 breakpoints in between. So lots of different p-value threshold possibilities. For each one of them, estimate the numerator of the FDR calculation, that capital F, the number of false positives. Compute the number of total positives. That's just the number of features that had p-values below your threshold. And then compute the estimated false discovery rate. And then we can make some pictures. So here is a picture. P-value cutoff on the horizontal axis and estimated false discovery rate on the vertical axis. The one, if we were to use 0.05, here's 0.1, there's 0.5-ish, and the false discovery rate associated with our 148 features that we pulled out based on having p-values less than 0.05. The FDR is a little above 0.2, looks like 0.2 or 0.25 or something like that. So I can say something like, here's my 148 features out of our 1,000. I think these are worth investigating. How confident am I in them? Well, I estimate the false discovery rate to be 0.25. So I expect no more than a quarter of those 150-ish to be false positives. Here's another picture, FDR estimate on the horizontal axis, and the number of features that you get into your list of selected ones on the vertical axis. So I mentioned last time that inspecting a picture like this can sometimes help you find where the balance, a good balance is between error and enough stuff to actually investigate. For these data, let's see. You don't get a lot out of these data. These are simulated data, so we could easily make this look differently. In fact, I'll do that in a second just for fun. But for these data, in order to get a substantial number of features, let's say over 100, that's not even 100 right there, but for nearly 100, you're going to have a false discovery rate of about 20%. That's a pretty high false discovery rate. If we were to change the simulation, like make it so that it's easier to see differences, let's keep the same number of differentially expressed features. We're going to keep it so that there's 3. But let's make it so that the ones that are differentially expressed are easier to see. So let's do 1 to 300 equals sample. And what's the mean difference going to be? In the current simulation, some of the differentially expressed features had a mean difference of -2. Some of them had -1. Some of them only had -0.5. And then some of them had positive versions of those. So I just randomly picked these differences. Let's make it more stronger differences, I guess. So let's make it be just -2 and 2. So any feature that's differentially expressed will have a mean difference in absolute value of 2, which is bigger than a lot of them that we currently have. So I'm going to rerun this code to generate some data and then create stronger differential expression. So if I increase the strength or the magnitude of differential expression, let's see what happens. Okay, that's the histogram of p-values now. If you remember what it did look like, it looked kind of more like this. By increasing the strength of differences between the comparison groups, it looks now more like that. In the real world, you don't know. Like in our case, we're playing pretend. We're saying we have 1,000 features, and I'm going to make the first 300 be the interesting ones, and everybody else is not interesting. That's a simulation in the sense that we're playing pretend. We're making up our own numbers. In the real world, you're right. We would only have our 1,000 features and then different columns for all the replicates in our study. And we would go through feature by feature and get a p-value, and then we could make these pictures. It might look like the left one or it might look like the right one. We don't know which goes into interesting, not interesting. So this FDR stuff that we're talking about can pick up right here. We don't have to know the answer that we know in this simulation. We pick up the FDR stuff and we look at these pictures and we say, my estimated proportion of uninteresting features is such and such. We can estimate that by just looking at the histogram. And by the way, do you think that estimate's going to be bigger or smaller in this one? Probably going to be smaller because we tightened up the differences. But I can estimate the proportion, and then I can use that to estimate a false discovery rate. So I don't have to know these magic answers in reality. We can estimate everything. So I have my 1,000 features. I don't know which one's interesting, which one's not. I compute p-values. I can convert those to a false discovery rate. And then I can say, for the top 150 features, say, ranked by p-values, my estimated false discovery rate is such and such. How's that? Is it still confusing?
Makes sense, but it might be trouble for someone like me who even getting to that point in terms of getting, if I had that sample spreadsheet, getting to that point, I wouldn't know the code for that, for example. And so unless, we say, here's this range and generate this number, I understand the concept behind it, but in terms of getting that R, I would have.
Okay, so like with a real data set, not clear yet how to do this. Is that,
Right.
Did I understand right?
I understand what a false discovery rate is and what p-values are, but I would need help, getting that out of the system.
Okay, so you'll get practice doing that this week, and I'll give tips as we go along. The next homework assignment includes doing this on a real data set. So let me introduce the next homework assignment while we're talking about it here. Okay. You're going to play with two real data sets in this homework assignment. One is called, I'm just referring to as the yeast data, and I'll introduce that to you, I think, on Wednesday. And the other is microarray data from, I'm calling them the cardiothoracic data. So on eCampus, I think that's the way I describe them, cardiothoracic. Click on cardiothoracic and then download the data. The actual data file is called this. It's gds4308.soft. You can open it in a text browser or a text editor, so like Notepad or WordPad or whatever. Open it up. In fact, let me show you what it looks like. So on eCampus, under data, these are microarray data, which you don't have to know everything about right now, but they are going to be M by N matrix of numbers. One row per gene, in this case. Our features are genes, and the columns are different individuals for which we got the data from, like mice or people. So I'm going to download cardiothoracic, and then I'll show it to you. 646 data. I'll just do right there. And I'm going to open this in a text editor. So on this computer, I'm going to use Notepad++. This is what we get. If I scroll down a ways, eventually I get to an M by N matrix of numbers. And so this is on line 99, starting line 99 of this .soft file. The first row in the actual data part starts out with something that should look familiar to us. It's an Affymetrix probe set identifier, 1007_S_AT. Second row is a different probe set. So for each of the thousands of probe sets on this type of array, we have a bunch of numbers. Each of those numbers corresponds to a sample or a replicate that we studied. Up above all those numbers is what we're going to call metadata. So somebody did a microarray experiment in which they ran 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 microarrays. So like those little chips that we saw a picture of, the Affymetrix chip, 10 separate ones of those were bought and run using the individuals from this study, which we'll talk about in just a second. Like, are these people or what? And what was the study design? So in the different columns, like the first column of numbers is called GSM 487045. If you look in the metadata, all this gobbledygook up at the front, there are rows that correspond to column names, like GSM 487045 is described this way. 6 pre SRC or source. This is diaphragm muscle, first biopsy taken as the diaphragm was exposed. If you look down at 487044, this is 6 post. The first one was 6 pre. This is 6 post. So this is diaphragm muscle, second biopsy, late in surgery. So I gave you a link in the homework to a website that describes these data in some detail. I'll let you look at that. But these data are paired data. So for each of 5 people, there was surgery carried out to obtain, to do something to do with the heart. And as the surgery was begun, so as the heart cavity was exposed, a biopsy was taken. At the beginning of the surgery, open somebody up, take a biopsy, and look at the genomic profile for this particular individual. And then late in the surgery, for the same individual, get another biopsy, get another tissue sample, and run them again. So these are paired data. The first column is individual, we'll call it individual 1, they call it individual 6, but the first person and a biopsy at the beginning of the surgery. The sixth column is that same person, a biopsy taken later in the surgery period. We have the individual coded 1 pre, individual 1 coded post, individual 5 pre, individual 5 post, and so on. So these numbers down here, let's look at the first gene. Line 99, probe set ID 1007 SAT. Looks like the HGNC code for that is DDR1. Based on the second column, I'm assuming that's what that is. We could look it up. And now I have these 10 numbers. Suppose we wanted to test, is this gene different comparing late in the surgery to early in the surgery? So think about, you do surgery on somebody, trauma happens. You cut them open, you expose their heart. Chances are something is going to happen at a genetic level. Your body is going to respond and say, we are in trauma. So generate proteins that know how to deal with trauma. Go form clots, fight off infections, do stuff like that. So we're going to have data where as soon as you open them up, probably nothing has happened yet at the genetic level. Later in the surgery, chances are some things have changed. Certain proteins have been turned up, others have been turned down in response to trauma. Okay, so suppose we want to test gene by gene. Is this gene different? Is it responding to trauma? What might you do? You have 10 numbers for this first gene, DDR1. You have 10 numbers. Yes or no, is this an interesting gene? What might you do? What would you do? Just forget about bioinformatics. Just think about Stats 101. You have 10 numbers. You want to test the null hypothesis that the mean expression level for this gene is different. Late surgery versus early surgery. What would you do? You could run a non-parametric test or a parametric test. Okay. Yeah, paired t-test would be a perfect choice. Two-sample t-test, might be the first thing that comes to your mind, but these are paired data because this column is the same person as that column. And what you learned in Stat 101 is when you have pairing, you have greater statistical power if you do a paired t-test than if you just did a two-sample t-test. So one thing we could do with these data is a paired t-test. I'd go to gene 1, take those 10 numbers, paired t-test, p-value. Go to gene 2, do the same thing. So in terms of turning the numbers like in a spreadsheet into an FDR, step 1 would be to read these N2R. And you're going to get practice with that in homework this week. That's going to include getting rid of all this gobbledygook up at the front. You don't need this. Once you're ready to compute p-values and stuff, you don't need this. You do need this to figure out like what column corresponds to what person. In this text file, you have that information if you just scroll through and look. You can find it. So what I would do is I would take this text file that my collaborator sent to me, and I would figure out how to get the numbers, like starting at line 99, into R. And then I'd do a two-sample or a paired t-test. Row by row, feature by feature, let's do a paired t-test. To get p-values, then you could make a histogram of the p-values like we made in the script. You could convert the p-values to false discovery rates. You could make a picture that tells you about the trade-off between false discovery rate and the number of features that you get. And maybe you decide that false discovery rate of 0.05 is okay with you. Then you have a subset of these thousands of features, the number, or however many of them that had that fit inside that false discovery rate 0.05 cutoff. Here's my interesting features. Estimated FDR is 0.05, so I expect no more than 5% of my selected features to be false discoveries. I'll show you, we'll do this once or twice as we go through the week, but hopefully that's helpful. I would read in the data, get rid of stuff that's not necessary for computing p-values, compute p-values, convert those to a false discovery rate, and then you have done what we were talking about. I don't know which ones are interesting and which ones are not, because these are not simulated data. Some of the features are interesting, some of them are not. All I can do is compute p-values and then convert them to a false discovery rate. There's lots of other things we can do with these data, by the way, before we even get to computing p-values. I jumped the gun a little bit by going straight to false discovery rates and p-values, but we're going to talk about more exploratory stuff as well, like let's do cluster analysis on these data. Do some of these samples group together naturally and others group together in different groups? We could also try to do that for the features themselves. Do some of the genes clump together and other genes clump together in different groupings? We can do what's called principal component analysis, which is taking what's essentially a matrix of numbers and extract summaries or simplifications or decompositions of that matrix of numbers that account for or preserve as much as possible of the total information in this matrix, but in a simpler picture that we might be able to interpret something from. That's hard to explain without doing examples. I'll show you several examples. But things like principal components and clustering, these are multivariate statistics techniques. Multivariate means instead of one variable, you have multiple variables. And because of correlations between variables, you will typically get a richer story, more insight, if you consider them all together like simultaneously, joint assessment as opposed to one at a time. Principal components, singular value decomposition, cluster analysis, these are common multivariate techniques that have good application in bioinformatics. I'll show you how to use them soon, probably starting Wednesday. I did want to try to finish the testing script so we can move on today. So let me just show you in 10 minutes a couple of things that are down below. One thing that I definitely want to show you is that in order to compute, say, a false discovery rate, I just showed you how to manually do it by computing the p-values, making a histogram, and then estimating that pi0 thing. We could plug it in to get FDR estimates. There is a built-in function in R that does it for you. So yeah, we did this as kind of a rough estimate that got us to being able to estimate the FDR. But if we come back up a little before, we computed p-values. So we have these 1,000 p-values for our simulated data. And there is a function called p.adjust. $p.adjust, which is a base function that comes with R, and it adjusts p-values. It's a little bit misleading, this word adjust, I think, because this does more than just like Bonferroni correction. It does Bonferroni correction, which is type 1 error adjustment, but it also does false discovery rate correction, which is a different quantity we've talked about. But if you have p-values and you want to turn them into FDRs, you can just call p.adjust and say method equal FDR. This will not be the exact same algorithm that I showed you over here, but there's several flavors that do essentially the same thing. So you're not going to go wrong by using this one. So let's do it and compare to our FDR estimates. So here we already computed FDR hat. We estimated the FDR. Let's also do FDR hat from p.adjust. P.adjust, I pass in my p-vals. I say method equal FDR. And let's plot the two against each other. So FDR hat, whoops, FDR hat versus little FDR hat. X and Y lengths differ. Length FDR hat 1000. Length capital FDR hat 100. Oh, what I really want is something called a Q value. We talked about this last time. What a Q value is what I think we just got out of p.adjust. Q value is like a p-value, but it's derived from false discovery rates as opposed to type 1 error rates. It's defined, we said briefly last time in that paper, it's the minimum FDR that can be achieved if you were to call gene I significant. So I don't really care that you know the formula here. This is how you can compute a Q value. I just want to compare them with what just came out of p.adjust. Because p.adjust is what I would recommend you use in practice. It's handy for quickly taking p-values and turning them into false discovery rates. I would just like to compare what it gives me to what I computed myself. So now let's plot what came out of p.adjust versus what we computed. And if they're not exactly the same, they're very, very close. Long story short, if you do omics data analysis and you have thousands of p-values, you can use p.adjust method equal FDR to get false discovery rates. You now have, it's a little bit misleading again, you now have a separate number for each of your features. We have 1,000 p-values. Now the result of calling this function, we also have 1,000 FDR estimates. Really, FDR is designed to apply to a specific set of selected features. We have 1,000 features, 150 of them had p-values less than 0.05. The false discovery rate is such and such. The proportion of my 150 that are false positive. That's what an FDR is. When you do p.adjust, you get out a number per feature. So these maybe shouldn't be called FDRs. These are really what we are calling Q values. All it is like an FDR that you put next to each of your features. And it is the FDR that would apply if you were to call that feature significant. Think of it like a p-value, but it's an FDR-like p-value. So if a feature, if a gene has a Q value less than 0.05, then it is statistically significant at an FDR of 0.05. So what you would do in practice, you'd go look at your data. Probably going to look something like this. These are microarray data, so you could have very different experimental designs underlying your data. But ultimately, you're going to have an M by N matrix most of the time. Features in the rows, samples in the columns. Let's go row by row and assess, is this an interesting feature? So step one would be to read these into R, or whatever software you're going to use. Step two would be to do an analysis of them, like to get a p-value for every single one of them. Step three would be to turn those p-values into Q values. And step four would be to filter out the interesting features. Like, I'm comfy with an FDR of 0.05. I'm going to give every one of these features a Q value estimate. and then let's pull out, here's the top genes at a false discovery rate of 0.05. All the genes that had Q values less than or equal to 0.05. That's your interesting list of features. There's a couple of other things in this script that I said I would spend some time on, so I will spend some time on them next time. One is they have to do with correlation. What happens if there is correlation between the columns in your data set, which would be the case in a couple of different ways. One, you have 30 mice, and each mouse is measured once a week for 2 months. So you have a separate column. You have multiple columns for the same mouse. You have multiple measurements on the same mouse, repeated measures kind of study, correlated data. So a 2-sample t-test or even a paired t-test, if you had like 6 different measurements on the same mouse, neither of those are applicable. If you took 645 with me last semester, we talked about correlated data analysis. You can do a regression model, for example, if you have time course data. So you'd have treatment and gender and age and maybe time on which things were measured. And now we're talking about doing that regression model for every single one of your features to get a p-value. So I'll show you I'll mention that a couple of times. Another way that this happens commonly in practice is if some of the columns are what we could call technical replicates as opposed to biological replicates. So if we want to study human beings and differences in genetic profiles between cancer and normal, say, we would like repeat human beings who have cancer, because that's like the population that we're trying to make inference towards. So if I had enough space and resources to accommodate 100 samples, you could think about, should that be 100 different people, or should that be 50 people measured twice each, or somewhere in between? Getting multiple people allows me to characterize biological variability in the population of all the people that we're interested in. Multiple measurements on the same person says nothing about that biological variability in the population, but it does tell us about technical variation in the process of turning their tissue sample into numbers. Both of those are important. You don't want either one of them to dominate things, or you won't be able to see anything. But you do want to be aware, if you have multiple columns in your spreadsheet, what kind of columns are these? Is this different people, or is this replicates of the same person? The answer to that will dictate what you do with them. If you had technical replicates, for example, we had 10 people with cancer, 10 people who are healthy, each person's measured 3 times. So we have 60 columns in our data set, but I should not go to gene 1 and do a 2-sample t-test with 30 and 30, because I don't have 30 independent observations in each of the 2 groups. This technical replication induces correlation, so I need to be more careful. One simple technique, if you had that kind of scenario, would be to just average the 3 samples for the same person. I have 10 people with cancer, 10 people with normal. Each person, I have 3 microarrays. Instead of doing like a correlated data regression model or something that's a little more complex, you could just take the 3 columns for individual 1, average them into 1 column. Take the 3 columns for individual number 2, average them, and so on. Now you just have 20 columns, and you can do a 2-sample t-test. And you still benefit from having paid for those technical replicates, because the variation overall has been moved down. By doing technical replicates and averaging them, you decrease that technical variation. So you get tighter, you get like more power if you do technical replication. So it is good to do technical replication. It makes your job a little bit more complicated. Simplest answer is to average those technical replicates, and you still benefit from having done that. The last story that I'll fill in a little more next time is we just talked about what if there's correlation between the columns? What if this correlation, well, this is the same question actually. What if there's correlation between the features, between the actual rows? So gene 1 and gene 2 and gene 3, that false discovery rate stuff that we talked about, taking a picture of the p-value histogram and turning that into false discovery rates, that assumes that the features are independent of each other. The genes are independent, or at least they're not highly correlated. And anybody who knows much about probably biology, molecular genetics and all that knows that's probably not true. That genes are not independent of each other, strictly speaking. If you turn one up, chances are, at least some of the time, you're going to turn another one down, or another one's going to go up with it. They don't completely act independently of one another. Formally, strictly speaking, that false discovery rate stuff says each of my tests are independent. So statisticians have worried about that. It's a lot harder to have robust statistical methods when there's correlation. So I'll show you a simple little simulation. The short story is, I think you have to have some pretty strong correlation before you have to worry about it. Correlation between the features. I think it has to be pretty strong before you have to worry about it. Everybody uses false discovery rate, even though the assumption is independence. Some people have done some simulations and stuff to say that what I just said. The correlation has to be pretty high before you worry about it. I'll show you that next time. And then we'll spend half of next time getting into some actual data analysis with data that you're using in your homework. I'll show you cluster analysis and principal components and stuff starting next time. Okay, questions?